Welcome, everyone. Today we have a really special deep dive for you, our engineering audience, into precision in plant design. And we're actually treating this exactly like a professional slide deck presentation.
Yeah, it's a great format for this because when you look at these massive industrial systems, you usually just see, brute force.
Right, just heavy machinery and concrete.
Exactly.
Yeah.
But underneath, it's this incredibly delicate balancing act of strict geometry. If you miss the mathematical skeleton, well, the steel will eventually fail.
Yeah, and our mission today is to unpack those exact geometric formulations that dictate, everything from equipment sizing to structural stability. So let's jump right in. On this slide, we're looking at the foundation, which we call the golden rule of geometry.
Right, the golden rule. So whenever you're dealing with a solid cone or a pyramid like a massive stockpile of crushed stone, the geometric center of mass, the centroid, always sits exactly at a height of h/4 from its base.
Just exactly at h/4 every time.
Every single time. And that one specific point is the invisible anchor for everything else. It tells you exactly where the distributed weight bears down on the tunnels below. But to even find that height, you first have to accurately forecast the volume.
Which relies on the static angle of repose, right? Like for crushed stone, gravity and friction mean it usually settles at, 16 to 18 degrees?
Yeah, usually right in that strict 16 to 18 degree pocket.
Okay, so finding that error for 4 mark is obviously crucial. But how does pinpointing that exact spot actually prevent catastrophic failures, like critical overturning moments?
Well, it all comes down to basic statics. If you don't know the exact 3D coordinate where that resultant force vector, the combined weight of all that stone is applying its load, then designing your structural brackets is basically guesswork.
Wow, so you're just hoping it holds.
Pretty much. Pinpointing h/4 ensures your calculated stresses perfectly match physical reality.
Okay, that makes sense. So moving to the next slide, we need to synthesize that complexity. Because in real-world plant design, we rarely deal with simple cones. We have complex composite bodies, like a hopper combining a frustum and a cylinder.
Oh, absolutely. And running calculus integrals for every complex transition piece is just computationally exhausting, which is why engineers rely on Pappus's theorems.
Pappus's theorems.
Yeah, they basically turn all that cumbersome calculus into simple multiplication.
I think I need a visual for that. Are we talking about, taking a 2D cardboard cutout of the hopper's cross-section and physically sweeping it through the air in a circle?
That is actually a perfect way to picture it. Pappus figured out that the distance the centroid of that 2D cardboard travels during that circular sweep gives you your exact 3D volume. You just multiply the area by the path length.
Wait, let me push back on that for a second. By collapsing complex calculus into just basic multiplication, aren't we risking a loss of structural precision in those real-world transition pieces?
You definitely think so, but the math is absolutely rigorous for surfaces of revolution. As long as your initial 2D centroid calculation is perfectly accurate, the resulting 3D volume is mathematically exact.
That is incredibly elegant. All right, well, moving to the next slide, let's apply this to stockpile dynamics and the tunnel variable, because we have to separate gross volume from net live volume.
Right, and that's a huge operational distinction. If you put just a single feeder under a static cone, your net live volume is only about 25% of the gross footprint.
Just 25%. And the rest is dead weight.
Exactly. But if you optimize that design to 4 feeders, you create a near rectangular draw footprint. Suddenly your net drawable volume jumped up to 38%.
That is a massive jump. And that brings us to the tunnel variable, which I find fascinating. This is where a minor civil works change totally transforms the math.
It really does.
Like, if you build a below-ground tunnel, the gross volume uses a cubic variable, basically h cubed. But an above-ground tunnel with a 2.5-meter retaining wall drops the math to a squared variable, h plus 2.5 squared. I mean, it's amazing how a minor architectural choice drastically reshapes the governing mathematics like that.
Well, think about the physical shape. When you put a 2.5-meter wall above ground, you're essentially chopping the bottom off your cone.
Oh, right, because it can't spread out anymore.
Exactly. The base of the stockpile is constrained by those concrete walls. Because it can't expand outward infinitely, the volume scales differently as height increases, which flattens the equation.
That makes perfect sense. Okay, on this slide, let's expand to dynamic moving equipment and mobile plant stability.
Right, so for mobile plants, the vertical projection of your combined centroid has to strictly remain inside the support polygon.
To prevent tipovers, right, like during grade parking or highway transport.
Yeah, and especially during operational crusher vibrations. It's what we call the cascade of geometry. Input variables dictate your volume.
Which then specifies the exact centroid location.
Right, and that ultimately dictates the engineering outputs, like your foundation bolt sizing.
Oh wait, static dead loads are predictable. How do unpredictable crusher unbalance forces change things compared to a static load?
That's the ultimate dynamic challenge. Crusher unbalance forces actively push that resultant force vector horizontally, shifting it away from the center line.
Oh, wow.
Yeah, if your static centroid is designed too high up, those dynamic forces will violently push the vector right outside the safe polygon, leading to dynamic instability.
Which means the whole thing could fail. So geometry really is the absolute foundational step of safe plant layout, not just some afterthought.
Every single time, the math dictates the physical reality.
I love that. Well, before we wrap up, I want to leave you with one final provocative thought. If crushed stone rests at a strict 16-degree angle of repose here on Earth, dictating all of these rigid geometric formulas, how might those exact stackable heights and equations transform for off-world mining operations in low-gravity environments? Think about that the next time you look at a massive stockpile.